Now slide and video both are visible,
Oh,
sir.
both. Okay, nice. No, that's okay now. Right, good. So, so we were talking about congestion control strategies. Of course, congestion control strategies, I have to, as I have told you in the last class, they fall into two categories: congestion prevention and congestion avoidance. Right. So, congestion prevention means not letting the congestion to happen in the first step itself, and whereas congestion avoidance is after detection of a congestion in the network or at a node, trying to overcome that situation or come out of that particular situation. That is congestion avoidance. So we broadly categorize them as open loop congestion control strategies and closed loop congestion control strategies. Open loop congestion control strategies were all discussed in the last class, previous class: a retransmission policy, window policy, acknowledgement policy, discarding policy, and admission policy. All these five policies were discussed in the last class. So that was congestion prevention. Coming to closed loop, congestion avoidance, again, the first two were also completed in the last class: back pressure, choke packet. And we are now left with implicit signaling and explicit signaling. So let us quickly start from back pressure again so that we can, recall what has happened in the previous class. It was on Friday, right? So these were all completed. Back pressure. Back pressure is from a particular source to a particular destination. The data is being, communicated, sent and received. And if there are few intermediate nodes in between, in my example, on my slide there, I have 4 intermediate nodes, 1, 2, 3, and 4. And I have assumed that there is a congestion at node 3. So in back pressure technique, what happens is node 3 will send a packet warning bit or a packet back to node 2. It applies back pressure, sends a packet to node 2 indicating the congestion at 3. Now node 2 will slow down. It will send less number of packets to 3. And at the same time, node 2 will also send the same warning packet to node 1, so that 1 will slow down sending packets to 2, and then 1 will send it to source. Then source will slow down sending the packets. So a step-by-step warning is sent from node to the previous node to the previous node until it reaches the source, and then once it reaches the source, the total communication gets slowed down. Once it reaches the source, the total communication gets slowed down. I mean, the sending of packets or the data traffic gets reduced from the source. That is back pressure. If you go to choke packet, instead of sending a packet from node to the previous node to the previous node and slowing it down step by step, in a choke packet mechanism, the congested node sends a warning packet or a choke packet straight to the source, which means not directly to the source through the intermediate nodes, but it is intended for the source only, which means if in my example, in between source and destination, if there are 4 nodes, 1, 2, 3, and 4, and if 3 is congested, now if 3 sends a choke packet, it goes through 2, 1 to source, but 2 will not slow down, 1 will not slow down. They will not even bother about what is the packet, because the address in that choke packet will be source address. Now it is intended for source, so it is simply forwarded until it reaches the source. Now source will slow down. If source will slow down, one will receive less number of packets, so one will slow down. If one will receive less number of packets, then obviously 2 will also receive less number of packets, and now 3 will receive less number of packets. This is the mechanism. So the difference between back pressure and choke packet is back pressure is applied step by step until it reaches the source. Choke packet is a packet that is directly intended for the source to cut down the data traffic. That is the difference. Okay. So anyway, whatever the technique is, the intention is to cut down congestion or overcome congestion, right? Avoid congestion rather, right? Then let's go to a technique called implicit signaling. What is implicit signaling? It's like something like you see, even humans will have their implicit mechanism. Sometimes you yourself will come to know that something is wrong and you stop doing it. You are eating some food. For example, say you are eating some food. There is enough food in the plate. You have, you started consuming. After a while, you started feeling like, no, I have too much in my belly. Though there is food available, you come to know for yourself that you cannot take any more. That is your instance there. That is your instinct there, right? So similarly, in implicit signaling, the source itself will come to a conclusion that there is a congestion. Nobody will, no back pressure, no choke packet, no other policy is adopted. Even before a policy is adopted, the source itself will come to a conclusion. It will have its own, thinking for whatever reason. It will come to a conclusion that there is a congestion in the data being sent, or in the path that is being sent, data being sent, and it slows down by itself. Nobody will tell it, right? So that's what it is. Implicit signaling. In implicit signaling, there is no communication between the congested node or the nodes and the source. There is no communication at all. The source guesses that there is a congestion somewhere in the network from other symptoms. For example, when a source sends several packets and there is no acknowledgement for a while, source is sending, keep going on sending packets, but even after a while, not even a single acknowledgement has come back. One assumption is the network is congested. Obviously, why wouldn't an acknowledgement come back? Wild assumption is obviously the first assumption would be the network is congested. The delay in receiving an acknowledgement is interpreted as congestion in the network. It could be a delay in the acknowledgement, or it could be a congestion for sure. But anyway, the source, in implicit signaling technique, the source will come to a conclusion that there is a congestion in the network. That is implicit signaling, and the source will slow down. That's what. Did you understand? The source itself will come to a conclusion that there is a congestion in the network, and by looking at the symptoms. What kind of symptoms? For example, delay in the acknowledgements. If the acknowledgements are not coming back in time, or acknowledgements are not coming back at all, then it assumes that there is a congestion, right? Then it slows down. That is implicit signaling. So that's the difference between your choke packet, back pressure, and implicit. Choke packet, back pressure, someone has to inform the source. Implicit signaling, no communication happens to the source, but the source itself will understand and come to a conclusion. That is implicit. Then explicit signaling. So what is explicit signaling? In explicit signaling, the node that experiences the congestion can explicitly send a signal to the source or destination. It is a little bit similar to your choke packet or back pressure, but there is difference. Little bit similar. So the node that is experiencing the congestion will send a signal either back to the source or to the destination. Why to the destination or why to the source? Anyway, the explicit signaling method, however, is different from the choke packet method. How? In choke packet method, a separate packet is used for this purpose. In back pressure, in choke packet, every one of them has their own mechanism. Now, if you think signaling and choke packet is same, it is wrong. In a choke packet, a separate packet to tell about congestion, a separate packet is sent to the source. But whereas in explicit signaling, no separate packet is sent. If there is any data that is supposed to be sent to the source, any data that is going towards the source, it adds this choke packet or this warning packet to that particular data that is going to the source as piggybacking and sends it to the source. That's the difference. It may look same. Choke packet will send a separate packet, warning packet to the source to inform about the congestion. Explicit signaling will not send a separate packet. Instead, it will add this choke packet or warning packet to the outgoing packet, outgoing data packet, as a piggybacking, as a tail to it, and sends it to the source. That's the difference, okay? So in explicit signaling method, the signal is included in the packets that carry the data that are going to the source or that are going to the destination. Explicit signaling can occur in either forward or backward direction. Two methods. In explicit signaling, again, there is backward method, forward method. Backward signaling, forward signaling. Then what is backward signaling? Sending a signal back to the source. Simple. What is forward signaling? Sending a signal to the destination. Let us look at backward signaling first. Backward signaling, a bit can be set in a packet moving in the direction opposite to the congestion. From where it is coming, it will now send a packet back, direction opposite to the congestion, which means to the source, right? So this bit can warn the source that there is a congestion and that it needs to slow down. to avoid discarding of packets. That is backward signaling. Right? Source will slow down. In backward signaling, source will slow down after receiving a explicit signal from the congested node. Now, what is forward signaling? A bit can be set in a packet moving in the direction of the congestion, which means towards the destination. Now it is being sent towards the destination. This bit can warn the destination that there is a congestion. Now what happens? What is the use? Source key manam warning is the bane because source will slow down, cut down the number of packets that it is sending. But if it is sent to destination, what is the use? There is use. Last two lines. The receiver in this case can use policies such as slowing down the acknowledgements to elevate the congestion, to avoid the congestion, to overcome the congestion. So what will happen if a destination receives warning? Destination will slowly send acknowledgements, which will delay the acknowledgements. What happens if it delays the acknowledgements? The acknowledgements will not come back in time. Then source may use implicit signaling, may understand that there is a congestion, it will slow down. Is that clear? So that is a technique called explicit signaling. So we have 4 techniques in congestion avoidance, very important 4 techniques in congestion avoidance. First is back pressure, where from the congested node, a warning packet is sent, to every other node in the direction that the data is coming until it reaches the source. Then the next one is choke packet. In a choke packet technique, a choke packet is directly destined or destinated to be received by the source. To the source it is sent directly, not the intermediate nodes. Through the intermediate nodes, but directly to the source. Done. Then comes your implicit signaling. No communication happens in implicit signaling. The source will somehow come to a conclusion that there is a congestion in the network and applies strategies. How it will come to a conclusion that there is a congestion? By looking at the acknowledgement. For example, if the acknowledgement doesn't come back for a while, or if they get delayed, then the source assumes that there is a delay or that there is a congestion. Then comes your explicit signaling. In explicit signaling, the congested node has to send a signal either to the source or to the destination. How is it different from choke packet? In choke packet, a separate packet is sent to the source. In explicit signaling, no separate packet is sent. Instead, a warning or a choke bit is added to the outgoing data in that direction. So explicit signaling again can happen in 2 ways, backward or forward. Backward is sending a signal back to the source. Forward is sending a signal to the destination, right? Then what is sending a signal back to the source does? Source will slow down. What happens if a signal is sent forward to the destination? Destination will delay its acknowledgement so that the source will slow down. So these are all your congestion avoidance strategies. Hope you understood this. Then can I go ahead? Did you understand what congestion is and what congestion prevention is and what congestion avoidance is? Can I go ahead? Right. Then now that is a general congestion avoidance. What I have talked till now is general congestion avoidance. But actually our layer that we are talking about right now, the unit which we are in is a transport layer level, right? So in transport layer level, what are the 2 most important protocols that we discussed about? User datagram protocol, transmission control protocol. In user datagram protocol, it is unreliable. It is, no connection at all. Can we talk about congestion when there is no connection at all set up? No. So we should now only talk about congestion control, especially in TCP now. So we are now talking about congestion control when transmission control protocol is being used. Again, one more important question, one more important topic for your examination. Done? Right. So TCP uses a congestion window and a congestion policy that avoids congestion. Previously, we assumed that only receiver can dictate the sender's window size. We ignored another entity here, the network. Source destination. We are only worried about source and destination, And if source and destination are happy, everything is fine. No, that's not the case actually. What about the network? The network itself should also dictate the terms. If the network is busy with data, because there could be, other than the source and destination, there could be other nodes that are communicating at the same time. There could be traffic over the network, right? So we cannot just only talk about source and destination. We have to talk about the network also. That is the third entity. And sometimes the network may also tell the sender to slow down, not the destination, not the congested node. The network may also tell the sender to slow down. The network is a second entity that determines the size of the sender's window. That determines the size of the sender's window. Okay. So now let us look at how congestion prevention happens in TCP, right? So let's talk about congestion policy in TCP. This is a simple technique. Again, there are 3 techniques in this, but very simple. Try to follow what I am saying. Very easy and simple to understand. Congestion policy in TCP, in Transmission Control Protocol. The first phase is called as slow start phase. It starts slowly. What do you mean by slow start phase? The sender starts sending the data packets, but slowly. That is the first phase. It starts slowly, and then increment is exponential. To the threshold, we'll put it aside. Increment is exponential. What does it mean? If it sends one packet first, what is exponential increase? Next it sends, if nothing goes wrong, no congestion happens, acknowledgement has come back successfully in time. What happens? The increment is exponential. Look at it again. Slow start phase. It starts slowly. Increment is exponential. So let us just say it starts with 2 power 0. So first one packet is sent. Everything is fine. Increment is exponential, which means 2 power 1. Next it sends 2 packets. Everything is fine. Then exponential increment, 2 power 2. Next it sends 4 packets. Next it sends 8, 16, 32. So the communication happens by using the first phase called a slow start phase in TCP. In a slow start phase, it starts slowly and then incrementation happens exponentially to the threshold. That is the last point. So if it keeps on exponentially incrementing, 8 becomes 16, 16 becomes 32, 32 becomes 64. But you cannot just keep incrementing like that, right? So there should be a threshold level where, what is the threshold level? The maximum packets that the network can handle at a given time. That becomes the threshold. So once it reaches the threshold, now what happens? Let us see. Then comes to the next phase called congestion avoidance phase. Can you see it there? Slow start phase, then followed by congestion avoidance phase. What happens in congestion? When does the congestion avoidance phase is reached? When it reaches the threshold. It starts slowly. It keeps incrementing exponentially until it reaches a threshold. Once it reaches a threshold level, it enters into a next phase called avoidance phase. In avoidance phase, after reaching the threshold, increment is done by 1, just additive increment. It's called additive increment, simple incrementation. Until it reaches threshold, incrementation is exponential. After it reaches threshold, the incrementation is 1. Increment is done by 1. Then the last phase is congestion detection phase. What does that mean? Sender kept incrementing. After exponentially incrementing, it entered into avoidance phase. It incremented 1, 1, 1, 1. Still, so for some reason, there is a congestion. It entered into congestion. Then it enters into the third phase called congestion detection phase. Once a congestion is detected, sender goes back to the first phase or the second phase. Either it goes back to slow start phase or it goes back to congestion avoidance phase. So this is how congestion control is implemented in TCP. Don't write mixed up concepts. Congestion prevention and congestion avoidance, if generally asked, you have to write the previous slides. Open loop congestion control and closed loop congestion control. You have to write those. If specifically congestion control in TCP is asked, you should not write any of those. I'll give you 0. They will not be considered at all for a single mark. If a question is asked on congestion control, especially in TCP, you have to write these: a slow start phase, a congestion avoidance phase, and a congestion detection phase, right? I'll explain them. I'll explain them deeply now. Let's go ahead. Let's go ahead with slow start phase. It is also called as exponential increment phase. That's what I told you, right? In this phase, after every RTT, round trip time, the congestion window size increments exponentially. What is RTT, round trip time? Can someone tell me from your OS? From your OS, what is RTT, round trip time? At least from networks. Okay, from our topic here. What is round trip time?
Turnaround time.
Turnaround time there, excellent. What is round trip time here then? What would be round trip time here? The time taken for a packet? Yes.
From sender to destination and destination to sender.
What is the destination to sender?
Time.
Acknowledgement.
Acknowledgement. Ah, that's what. The time taken for a data packet to be sent from source to destination and an acknowledgement to come back. For that packet, an acknowledgement to come back from destination to source. This overall time is called as round trip time. So initially look at that algorithm now. Initially, CWND means congestion window. What is the size of congestion window? 1. What does that mean? It can send only one packet at a time and it should wait for the acknowledgement to come back. That is a slow start phase. So once the packet is sent and the acknowledgement is come back, what do you call it? Second line. That in that my algorithm there, second line. After one RTT, what does that one RTT mean? First round trip time is finished. What is first round trip time? One packet is sent and acknowledgement has come back. After one RTT, CWND is equal to, what is CWND? Congestion window. Congestion window is equal to, now 2 power 0 gets incremented, 2 power 1. Exponential incrementation. It becomes 2 power 1. What is 2 power 1? 2. So after one RTT, the congestion window size gets to 2, exponentially incremented. Now 2 packets can be sent without waiting for an acknowledgement. What is the difference between congestion window is 1 and congestion window is 2? What is the difference between window size equal to 1 and window size equal to 2 according to your flow control and data link layer? What is the difference between window size equal to 1 and window size equal to 2? Do you remember stop and wait, go back, N algorithms? Selective repeat. Now tell me what
can be sent
2 packets can be sent
without waiting for acknowledgement.
without waiting for an acknowledgement. If window size is equal to 1, only 1 packet can be sent before an acknowledgement comes back. If window size equal to 2, 2 packets can be sent without waiting for an acknowledgement and then stop for an acknowledgement, wait for an acknowledgement, right? So that is your second step. Then the third step, after 2 RTT, second round trip time is finished. Now the congestion window increases exponentially. CWND is equal to 2 power 2, which is 4. Now the sender can send 4 packets without waiting for an acknowledgement. Of course, that is also successful. Then after 3 TTT, third round trip time, congestion window becomes again exponentially incremented, 2 power 3. It becomes 8 now. So 8 packets can be sent without waiting for an acknowledgement. Then until when this should happen? Until a threshold is met. A threshold is predefined. We don't want to fix anything right now. A threshold is any number that is predefined, fixed before. Okay, so that is a slow start phase. It is also called as exponential increment phase, remember. Then after a threshold is met, then it enters into second phase called congestion avoidance phase. This phase is also called as additive increment phase. First phase is exponential increment. Second phase is additive increment. So in this phase starts after the threshold value is denoted as SSS thresh. SS means slow start. Thresh means threshold. Once it is met, once the SS threshold, we have to write this in the program if required. SS threshold means slow start phase threshold value is met. Then what happens? The size of CWND, last second line. The size of CWND means congestion window. The size of CWND increases additively. That is, after each round trip time, CWND is equal to CWND plus only 1. Whereas in the slow start phase, the increment was exponential. In congestion avoidance phase, the increment is additive. Only one increment happens. I just don't want to show it. Additive increment, right? Plus plus, simple plus plus. Then now still you went on incrementing 1, 1, 1, 1. There is some stage, if no congestion occurs, all the data is communicated, that is really nice, well and good. But at some stage, if congestion occurs, then it enters into the third phase called congestion detection phase. Now the congestion gets detected. Now what is this phase also called as? Earlier phases, incrementing phases until congestion is met. But this phase, once congestion is met, it should be a decrement phase. We cannot still keep sending packets, right? You have to decrement the number of packets that are being sent. So this phase is called as multiplicative decrement phase. No additive, no exponential. It is multiplicative. See the difference. So now look at this. If congestion occurs, the congestion window size is decreased. As obvious, it has to be decreased. The only way a sender can guess that congestion has occurred is the need to retransmit a segment. So how to understand, how the sender understands? Sender was in slow start phase. Sender entered into additive increment phase. When will sender decide that it should enter into a congestion detection phase? It should understand that there is a congestion. And how can it understand? If it is retransmitting more and more segments. Retransmission of segments. What does that mean? Acknowledgements are not coming back. What does that mean? There is a congestion. Assumption, right? So the only way a sender can guess that congestion has occurred is the need to retransmit a segment. Retransmission is needed to recover a missing packet, which is assumed to have been dropped by a router because of congestion. That's what it is. Why do we retransmit a packet, segment, or a frame? If it is lost over the network, in the network. Why is it lost in the network? A router might have dropped it. Why will it drop it? Because it is congested. It is overloaded. Right? So now let us look at when a retransmission can happen by the sender. When a retransmission can happen. Retransmission can occur in one of these two cases. When the RTO timer times out, or when 3 duplicate ACKs are received. Right. Let us talk about the first one. What is an RTO timer? I have written there, case 1. Retransmission due to timeout. RTO. Retransmission due to timeout. What is retransmission due to timeout? You remember, sender sends a packet or a frame in data link layer. Sender sends a frame. It starts with timer. It's timer. And if the acknowledgement comes back before the timer is out, it sends the next packet or next frame. If an acknowledgement doesn't come back and the timer expires, what happens? Acknowledgement resend. That is retransmission due to timeout. Timeout avadam valla retransmission jarigindi. Now, if an acknowledgement doesn't come back, timer has expired. Do you think there is a congestion in the network? The chances are high. Assumption, yes, there could be a chance. The chances are high. So, case 1, retransmission due to timeout. In this case, congestion possibility is high. Then what should happen? This is what will happen. 3 steps now. I am talking about an algorithm, implementation of congestion control in TCP. And I'm now talking about the third phase, multiplicative decrement phase. In that, if retransmission happens due to timeout, what should the sender do? 3 steps. First step, SS threshold. What is SS threshold? The first step, slow start phase threshold level. Maybe that is very high. It is reduced to half of the current window size. Now, whatever the window size was when congestion has encountered or assumed to be happened, then what happens? The first step is that congestion windows, the threshold level is reduced to half. That's the first step. Second step, again, set congestion window to 1. What does the 1 mean? 2 power 0, which means you are starting with the first phase again. When is your congestion window size 1? Initially, first, beginning the congestion. Can I go back and show you? See there, initially, CWND, congestion window is equal to 1. So what are you doing once a RTO happens? First threshold level is reduced to half. Then congestion window size is brought down to 1. Then if congestion window size is 1, obviously third step, start with slow start phase again, so that you start avoiding the congestion. Slowly you can increment exponentially and then additively. That is how you overcome a congestion if congestion is identified by RTO, retransmission due to timeout. If congestion is identified by second case, retransmission due to 3 duplicate acknowledgements. Now, when do you get a duplicate acknowledgement? When do you get a duplicate acknowledgement? Frame 0 is sent, received. ACK1 comes back. Okay, ACK1 comes back. ACK1 somehow is lost or whatever happens. Frame 1 is also sent. Frame 1 is lost. Frame 2 is sent. Because in go back and selective repeat algorithms, we can keep sending frames, right? Frame 2 is sent. Frame 2 is also lost. Now, after a couple of losses of or damaged frames received by the receiver, it will send ACK1 again. So duplicate acknowledgements most likely doesn't mean that there is a congestion. Timeout, yes, there is high probability that there is a congestion. But a duplicate acknowledgement happens mostly because of other reasons. Done? So the second case, retransmission due to 3 acknowledgement duplicates. In this case, congestion possibility is less. I'm not saying no congestion. I'm saying possibility is less. In first case, congestion possibility is high. Remember this for your objective questions. In RTO, if the congestion is identified or anticipated because of RTO, the chances of congestion being present is high. If anticipation of congestion happens because of case 2, the anticipation levels or the chances of congestion being present are less. So what happens if chances are less? What should you do? Again, a 3-step procedure. For case 2, again a 3-step procedure. Again, the first step is same. The slow start threshold value reduces to half the current window size. Window size gets reduced to half. Then set congestion window size not to 1. Instead, set it to SS threshold, which means a better value, not an initial value. Because why did you set congestion window to 1 in case 1? And why did not you set congestion window to 1 in case 2? What could be the reason?
High possibility.
Yes, that's it. Very simple. Because of high possibility in case 1, we have set it to the least size of the window. Because of very low or low possibility, not very low, low possibility in case 2, we have set the congestion window to a better, not to a least possible situation, to a optimum possible situation, the threshold value. And what happened to the threshold value? Threshold value was cut to half. Remember that. The first step itself, step A itself is SS threshold value reduces to half. Then we are setting congestion window to SS threshold, slow start threshold level. Then which stage are we starting with now? Is the congestion window equal to 1? No. So which means it is a congestion avoidance phase. So you either start from slow start phase, or you start from congestion avoidance phase. How do you decide which phase? Case 1, slow start phase. Case 2, congestion avoidance phase. Hope you understood. Right, I'm going back again. 3 steps in TCP congestion control policy, avoidance policy, 3 steps: slow start phase, congestion avoidance phase, and congestion detection phase. Slow start phase is also called as the exponential increment. We start with CW and D is equal to 1, and it gets incremented exponentially until a threshold is met. Once a threshold is met, SS threshold is met, we enter into it enters into a second phase called congestion avoidance phase, where the increment happens additively. The congestion window gets incremented by 1. Done? Then even after that, if a congestion is detected for whatever reason it is, there could be 2 reasons. The timeout happens or duplicate acknowledgements are coming back. In first case, we have to cut down the window size to half. We have to initialize the congestion window back to 1, and we have start from slow start phase. In the second phase, again, the congestion window has to be cut into half size. Congestion window size, sorry, threshold level should be cut down to half. Congestion window size should be now made equal to threshold level. Then we start from the second phase called congestion avoidance phase. That's about congestion control in TCP. Hope you understood it. Congestion control by itself is different and congestion control in TCP is different. Don't mix up the answers. Then I have one more topic. Now congestion control in frame relay networks. A frame relay network, actually you are supposed to have this in your syllabus. Frame relay should have been a topic actually, ATM especially, should have been a topic by itself in the syllabus, but your syllabus, I have seen twice, thrice, because I expected that it will be in the syllabus. It is not there in the syllabus, but unfortunately you have congestion control in frame relay. Frame relay is not present, but congestion control in frame relay is present in your syllabus. So let us just quickly go through. It's again a different type of network where data is sent and received. That's it. Where there is no, the only thing is how the network works is changed. Okay. So congestion in frame relay decreases throughput and increases delay. Generally, delay should be less or more in a network. In a network, delay should be less or delay should be more. Should the delay be less or should the delay be more? Come on. In a network.
Less.
Less. Okay. Why wouldn't you answer them? Should a throughput be more or less? What is throughput?
CPU.
Yes. Should it be more or less?
More.
More. So delay should be less and throughput should be more. Generally, any network, delay should be less, throughput should be more. But what happens, the first step itself, look at what happens in frame relay if congestion is there. Congestion in frame relay decreases the throughput, which is bad, and increases the delay, which is bad again. Actually, a high throughput and low delay is the main goal of frame relay protocol. That is the main intention. High throughput, low delay is the main intention, but congestion is reversing it. More delay, less throughput. Right? So the problem in frame relay is second point. Frame relay does not have flow control and it allows user to transmit burst data. That is the difference between your general transmission and frame relay transmission. In a frame relay, there is no flow control at all. What is flow control? Do you remember in data link layer we had it? ARQ mechanisms. Right? In frame relay, it does not have flow control. So if it does not have flow control, what happens? How many data frames can be sent without waiting for an acknowledgement? No rule. If there is no rule, what happens? The sender sends burst data. What is burst data? Send loads of data at once. There is no rule, right? Second point is frame relay does not have flow control and it allows user to transmit burst data. This means that a frame relay network has potential to be really congested with traffic and it requires congestion control. So obviously a TCP has less chances of congestion, but if you come to here in a frame relay network, because there is no flow control, since burst data can be transmitted, communicated, there is very high chance of congestion to happen in the network. Right? The last point, frame relay uses congestion avoidance by means of two bit fields that are present in the frame relay frame, in a frame. We already knew PPP frame, we already knew HDLC frame, we already know a normal data link layer frame. Now we are going to look at a new type of frame called frame relay frame. Though it is not in the syllabus, we'll just have just a overall look on the frame type. We will concentrate on those important parts of the frame which we need for congestion control. Is it okay? Right? So let us look at a new frame. Anyway, so last one, frame relay uses congestion avoidance by means of two bit fields present in the frame to explicitly warn the source and the destination about the presence of the congestion. They are BECN and FECN. Backward explicit congestion notification and forward explicit execution. I just had some water. Okay. So this is BECN and FECN, backward explicit congestion notification and forward explicit congestion notification. These are the two fields which we should stress on. And even in the examination, if congestion control is asked in frame relay, we have to stress on those two fields. We have to draw the frame, we have to show where they are, then we have to explain what they are, right? So let us look at the frame first. Frame relay. Now I am showing you the frame format. Generally, this is supposed to be in your syllabus. It is not there in your syllabus, but without knowing this, you cannot understand congestion control in frame relay, right? Remember the frame format of HDLC? It starts with a flag, ends with a flag. It has a control, it has an address field, it has a control field, it has a payload field, it has an FCS field. Do you remember? Then if you remember the frame format of PPP, starts with a flag, ends with a flag. It has an address field, it has a control field which is always 1160. Then it has one more field called protocol field. C223, C023, 8023, 8223, remember? LCP packets, NCP packets, IP packets, authentication protocol packets, password authentication packets, challenge handshake authentication protocol packets. That was all about PPP frame format. Now, if you are talking about a frame format which is in frame relay network, any frame will start with flag, end with flag. That is by default. At least you want to get 1 or 2 marks for an answer for a frame format. Remember these 3 things. It starts with, 4 things, obviously common for all. The first 2 fields and the last 2 fields are common for each frame. Any frame type, may it be HDLC, may it be PPP, may it be your normal frame, which is not related to any protocols, may it be your frame relay. The first 2 fields and the last 2 fields. Starts with a flag, ends with a flag. Those are the 2 fields, first and last fields. You can see it here also. Starts with a flag, ends with a flag. After the flag, the next field is always address. In HDLC, it is address. In PPP, it is address. Here in frame relay, it is address. The senders and receivers address is present there. Before the ending flag, the field is always error detection field, error detection and correction field, FCS, frame check sequence. Did anyone till now see any other fields in the first 2 and the last 2 positions apart from these 4? If anyone has seen, please respond. If not, I'll take it. There is no field, and there is no other field apart from these 4. So always remember, first 2 fields will be flag and address. Last 2 fields will be FCS and flag. And obviously there should be information. So 5 fields are mandatory. For a frame, these 5 fields are mandatory. HDLC will have 1 additional field called control field. PPP will have 2 additional fields called control field and protocol field. That's it, right? So now here also, look at it. Look at it. The frame format starts with a flag, ends with a flag as usual. What is a flag? 0610, which is used to identify the beginning and ending of the frame, or to identify the next frame's start. Then, of course, FCS, frame check sequence. For every frame, there is FCS. It is used to identify errors, detect the errors. It could be either checksum, it could be CRC, it could be anything, any error detection and correction technique. Information is the information that is being carried by the frame. The most important field in frame relay, because it does not have any flow control, So the most important field in frame relay is address field. Here is my question. What is the most important field in HDLC frame format? Anyone in the class? What is the most important field in HDLC frame format?
Maybe address.
Address. How many types of frames we have in HDLC?
I frame, S frame.
and U frame. Nenu, Novu, yes. I, U, and S. Okay? 3 frames. How did you identify if it is an I frame or U frame or S frame? Which field helped you? You're answering perfectly. Sultan, right? F3, right? Am I talking to F3?
Yes, sir.
Yeah, right. Sultan, you're going in the right way. How did you identify whether it is a U frame or S frame or I frame? Which fields helped you? There is a field called control field. If the first bit is 0, it is I field. If the first bit is 1 and second bit is 0, it is S. If the first bit is 1 and second bit is 1, that is U frame. So the most important field in HDLC frame is control field. What is the most important field in PPP frame format? Anyone in the class? Guess it. Try it. If you know, tell it. Don't put it inside yourself. What is the most important field in PPP frame format? How did you identify whether it is a LCP packet, whether it is a NCP packet, whether it is AP packet, SAP packet?
Protocol field.
Protocol field. Thank you, Manoj. Protocol field is the most important field. Control field in PPP, it was fixed, 1160s, always fixed. It is a U frame, always U frame, unnumbered frame. Okay, right. So here in frame relay, the most important field is address field, especially for congestion control. Now look at the address field. Address field is 16 bits, totally 16 bits, and I have given you the classification of all 16 bits there. First 6 bits, DLCI, data link connection identifier. 1 bit is C by R, 1 bit is EA. Again, 4 more bits for DLCI, which means 10 bits together. 10 bits for DLCI, data link connection identifier. Then comes your FECN, BECN. Now I'm going back. What are the 2 important bits, last 2 lines for congestion control in frame relay? BECN, FECN. This is where I have them. The yellow boxes, last 4 yellow boxes. FECN, BECN, then DE, discard eligibility, then EA, extended address. All the full forms I have written on the top there. You can see it. C by R means command or response. EA means extended address. BECN means backward explicit congestion notification. FECN means forward explicit congestion notification. DE means discard eligibility. DLCI means data link connection identifier. So which are the 2 most important fields for us for congestion control in frame relay? The 2 bits, single bit fields, FECN, BECN, forward explicit notification and backward explicit notification. But let us quickly look at all of them. Though it is not in your syllabus, let us just quickly look. We don't have to stress much on them. DLCI, data link connection identifier field. It is of 10 bits together. First 6 bits, then 4 bits. So the first part of DLCI is 6 bits and the second part is 4 bits. They together form a 10-bit data link connection identifier. The identification of the connection is given by these 10 bits, right? If I recall, if I have to give you an example, let me try and quickly recall what could be a connection identifier here, especially. It could be, I'm unable to recall quickly right now. I should have written it there better. Okay, go to the next one. Command response, the C by R bit. It allows the upper layer to identify a frame as either a command or a response. It is not used by frame relay protocol. It is not used, so we don't even have to worry about it. Just remember the field is C by R field, command response field. Can someone tell me where is this used? Which protocol did you come across this? Command response, in which protocol did you come across? There are 2 modes of communication. Asynchronous balanced mode, normal response mode. HDLC. In HDLC, there are 2 ways of communication. One is normal response mode. The second type is asynchronous balanced mode. In normal response mode, one device will always send a command. The secondary device will only respond. Command response. In a asynchronous balanced mode, both the devices can send commands. Yes. Then why did you forget all this? You are listening. People are listening. I feel as if they are listening. Or is it my interpretation that you are listening? Or am I just assuming? Am I being an illusion that you are listening to me? You have answered very good in that class. I still remember. నాకు గుర్తుంది ఆ క్వశ్చన్ అడిగితే మీరు చెప్పిన నాకు the next class లో. Right. So command response field anyway, it is not used in frame relay. So we'll just put it aside. We know that it is a command and response field. Then the third one is extended address. The bit indicates whether the current byte is the final byte of the address. How? If EA equal to 1, if this bit is equal to 1, this byte is the final byte. Address is done with this. If EA is equal to 0, the address is not done yet. There is one more address byte. The length of the address is more. Extended address. That is EA bit, sorry. Then comes your two most important bits. Forward explicit congestion notification, and the next one is backward explicit. Let's talk about FECN. Forward explicit congestion notification. This bit can be set by any switch to indicate that traffic is congested in the direction of travel of the frame. If a switch in between or a device in between will set this bit to 1, what will happen? As the frame is going forward, every other node that is receiving this data, this frame, will understand that in this path there is a congestion. It is going forward. It is going forward. Okay. FECN is used to warn the receiver. That's why it goes forward. It is used to warn the receiver of congestion in the network. It might appear that a receiver cannot do anything to relieve the congestion. However, the frame relay protocol assumes that sender and receiver are communicating with each other when it receives FECN bit as 1. Receiver delays the acknowledgement. Simple. Whenever receiver understands that there is congestion, what will the receiver do? It will simply delay the acknowledgement. If a sender understands, it will slow down the sending packets. Number of packets to be sent will be slowed down. If a receiver understands, it will delay the acknowledgement so that sender will slow down. Right? So that is FECN. A switch. Can someone tell me? Until now, I have been talking a router, intermediate node is router. Now I suddenly am talking a switch. Can someone tell me why I am saying a switch here? Why I was talking about router earlier? Anyone who is smart in the class? Which device works at data link layer level? Which device works at network layer level? Name a device that works at data link layer level. Name a device that works at network layer level. Which means if the data goes into the device, hardware device, it goes up to data link layer and comes back again. If it is not the intended receiver, it comes back out of it. If it is another device, the data goes up to network layer and comes back again if it is not the intended receiver. In your labs,
router at the data link
uh,
destination device will be at the network.
In your labs, generally in our SR Engineering College labs, in every lab corner, some other place, you will see a device with a lot of LAN cables coming out of it. It has lot of ports to plug in, lot of LAN cables coming out of it, and every LAN cable coming out of each port or each outlet will go to a computer. What is the device?
Switch.
Thank you. Switch. Now, will a switch work at data link layer or network layer level?
Data
Link layer level. That's what. Data link layer level. Right? So since I am talking about a frame here, what is the device I should talk about? What frame means which layer? Data link layer. What device should I talk about? Switch. Now, in your homes, if you have a Wi-Fi connection, what is the device you are having? to get connected to the internet. What is the device you are having?
Router.
Router. Router works at which layer?
Network.
Network layer. That is the difference. That is the difference. Okay. We have switches and routers we used to have in old syllabus. I don't know why it is missing now. Right? We only had a hardware, how a switch looks like. I've shown you how a crossbar switch is, multi-stage switches. You remember? N folded switch, N by N folded switch. In second unit, if you go back and see, you will find it. Forgot. It's gone. I know. It's evaporated out of your mind. So we didn't have that, differences in the syllabus, but still anyway, you have to know it. As a network student, you should know data link layer level, the device that works is switch. That's why in your lab, they are directly connected to your PCs. From this switch, they are connected to your PCs. Done? Then at network layer level, it is router that works. Okay? So that's why I'm talking about switch here. Now, anyway, what is FECN? Forward explicit condition notification. If this bit is set to 1 by any switch in between, any switch can set it to 1. When will it set to 1? If it finds that there is a congestion at it, it will make this FECN bit to 1 and it will send the packet. It will send the frame as it is. It will not change anything else. Only in the address field of frame relay frame, in the FECN bit, it is made 1 by the switch. So that the next device that is receiving the same frame will understand that there was a congestion in that path in which this frame has come. So what happens? If it reaches the router, if it reaches the destination will delay the EXOR because it came to know that there is a congestion in this path. That is how FECN works. Then go to BECN, backward explicit congestion notification. This bit indicates the congestion in the direction opposite to the direction of the frame travel. It is in the opposite. BECN warns the sender of congestion present in the network. This is achieved by resending the frame in the reverse direction of the BECN. Right? So FECN helps the destination to understand, BECN helps the sender to understand. Just like your TCP, in TCP explicit congestion, again you had forward signaling and backward signaling. Same thing here. Forward explicit congestion notification, backward explicit congestion notification. Forward to warn the receiver to slow down the acknowledgements, backward to warn the sender to slow down the frame relay segments or frames. Done? This is how congestion is controlled in frame relay networks by using two single bit fields called FECN and BECN. Then the last one, I think 6 is the last, yeah. Discard eligibility. Frame can be discarded or cannot be discarded. If DE is equal to 1, that frame has the least priority, rather, not probability, least priority and high probability to get discarded. If DE is not set, which means that frame need not be discarded, cannot be discarded. Simple. So here is the diagram for you. That is a frame relay network. And there are switches. All those are switches. I told you simple cross is a router. Like that is a switch always, right? Like that is a switch. So I have a sender and a receiver. Now in between is my frame relay network. That is all my network. In the network, I have switches connected to each other. Now that top, you can see that red line. There it is the congestion that is occurring. If FECN is set to 1, FECN is sent in the forward direction to the destination receiver. See where it goes? It goes to the next switch, to the next switch, to the receiver. Receiver understands that there is a congestion. Done? Then if it is BECN, backward explicit congestion notification, it is sent to the source, back to the source, from the same switch back to the source. Done? Right. So who is, now I have a question here. Who is informing about the congestion? A switch. How is it informing? The data that is going through that switch, in that data, in that frame, in the address field of that frame, if it wants to send back to the source, In BECN, it puts 1. If it wants to send to the destination, in FECN, it puts 1. Did you understand this? It can warn either the source or the destination that it is congested. Done. So here is an example. There are 4 cases. There are 4 cases. Look at the first case, A. From A to B, I have given 4 fields. One is that is going towards A, to the source. The other is going towards destination. Can someone tell me what it is? Towards A. Towards A. FECN and BECN both are 0. What does that mean? There is no forward congestion towards A. There is no backward congestion towards B. In the direction from B to A. In the direction from B to A, there is no forward congestion. There is no backward congestion. Bit. From A to B is the next one. Second yellow rectangle in the same field. FECN is equal to 0 and BECN equal to 0. In this direction again, FECN no congestion, BECN no congestion. That's why case A, what is it? No congestion at all. No congestion at all. Now look at B. From B to A, FECN equal to 0. What does that mean? No forward congestion. No forward congestion. Ante towards A, from that switch towards A, there is no congestion. BECN equal to 1 backward, which means from that switch towards B, there is congestion. Back. Now look at the data from A to B. Now A to B. FECN equal to 1, which means towards B forward, there is congestion. Of course, adjective backward, adjective forward. Towards A backward, there is no congestion. So in which direction the congestion is present? In which direction the congestion is present? Congestion on the bakada. Can't you even see that? Just those ones and zeros, you can't even answer what they are. And it is clearly written there under that diagram. Congestion in direction A to B. Come on. At least are you understanding? Please let me know. If not, I'll stop the class here. It's of no use shouting for 2 hours. No answer for this also. Good. Right. Let's go to third case again. From B to A, FECN is 1, BECN is 0, which means there is a congestion towards A. From A to B, forward is 0, backward is 1, which means there is a congestion towards A. So there is a congestion towards A, which means congestion is from B to A. Congestion is in the direction of A. Second case is congestion is in the direction of B. Third case is congestion is in the direction of A. Look at the fourth case, all are ones. So there is congestion forward and backward. So from A to B there is congestion, and from B to A there is congestion through that switch, right? So that's the importance of FECN and BECN bits. So that's about congestion control in frame relay networks. So we discussed congestion prevention policies, which is retransmission policy, window policy, acknowledgement policy, discard policy, no admission policy. Then we discussed about congestion avoidance policies or strategies, which are warning bit, it is actually back pressure. Instead of warning bit, it is called back pressure, choke packet, then forward implicit signaling and explicit signaling. Explicit signaling again had 2 types, forward and backward signaling, right? So that was about congestion, general congestion prevention and control policies. Then coming to congestion control in TCP, we had 3 phases: slow start phase, congestion avoidance phase, then congestion detection phase. In a slow start phase, it's also called as exponential increment phase, where the window size starts with 1 and then it gets exponentially incremented until it reaches a threshold. Then it enters into a phase called congestion avoidance phase, where the window size gets additively incremented by 1 plus 1 Then if a congestion is encountered, then because of two cases, because of two reasons. For the first reason, if a congestion has encountered, there is the possibility is high, which is RTO. Because of timeout, the congestion is high. So the threshold level and the window size is made to 1 directly, and we start from the first phase called slow start phase. And in the second case, we make the threshold level to half, and then we set the congestion window to threshold level, and we start from the second phase, congestion avoidance phase. That was about TCP congestion. Then we talked about frame relay congestion control mechanisms. There are two fields in the address field of a frame relay frame called FECN and BECN, forward explicit congestion notification and backward explicit congestion notification, which help in identifying the congestion and the direction of the congestion between a source and a destination. That's about congestion. Can I move ahead? I wanted to finish this entire chapter today. Then it's quality of service. It's not just congestion that is important. Apart from preventing and avoiding the congestion, the quality of the service has to be high. It is not just delay. It is not a delay that is just important. There are a lot of other factors that support the quality. Only delay is not always an issue. Delay is definitely an issue, but just delay is not enough. So our next topic, of course, at least pay some attention from now on. It is a bit interesting again. I don't know why you are not following FECN and BECN. That was very simple. Anyway, this is interesting again. Quality of service is a networking issue, internet issue that has been discussed than more than defined. We can informally define quality of service as something a flow of data seeks to attain, not the delay, not that. It is just something that the flow of data should attain. And what will it attain, right? Please pay attention from now on. Again, I'm telling you, if this question comes in the examination, you are one of the luckiest persons, because these algorithms, or not algorithms even, these techniques are very simple, straightforward techniques for you to understand. Then what are those characteristics? What do you mean by quality? How do you define quality? There are 4 characteristics I would define to talk about quality. They are called as reliability, delay, jitter, and bandwidth. These are the flow characteristics that are supposed to, 4 flow characteristics that are supposed to be present to assure a quality of service. What is reliability? Namakam. If I call you and if I keep talking to you, I should be reliable on the network that my data goes to you perfectly. If I stress a word, it is stressed to you. If I speak a word in low voice, it is in low voice to you. However it is a reliable communication that is happening between sender and receiver. Reliability, namakam, that it is sent and received. Data is communicated properly. That is not enough. Reliability is not enough. There is one more thing, delay. There should not be a delay. How many times you got irritated while talking over a phone when the response is delayed? You talk and after a while the person receives it and then he responds by the time you start talking again. Did this happen to you? Is there anyone who faced such a situation? Especially in international calls. Anyone?
Yes, sir.
Nobody faced it?
Yes, sir.
Yeah, it's quite common. Then do you think if there is delay, reliability is there? Don't you think reliability is there? Don't you think the data is being communicated to the sender? It is going there. But what is the other characteristic? Delay. Delay is the second characteristic there. Done? So delay should be less or negligible or sometimes zero. In some cases, there is no tolerance for delay at all. No delay should be there, especially phone call, especially video call. Do you really think there should be 1% delay? There should not be a delay at all, right? So that's the second flow characteristic. Reliability is not enough. Of course, even delay without reliability is waste again. No delay without reliability. So both of them. Then we'll go to the last one first, and then I'll come to the third one. Bandwidth. Enough bandwidth is not provided. Do you really think you'll have less delay? No, the delay will be more. Right? So bandwidth is the third important flow characteristic. Required bandwidth has to be available so that the communication is perfect, the flow is perfect, fast. Right? Then the fourth characteristic is jitter. What is jitter? Right? Jitter is something a little bit different to understand here. Look at this. Look at this. There are 4 frames transmitted. 1, 2, 3, 4. One after the other, 4 frames are transmitted. Generally it takes 20 seconds, 20 milliseconds for this packet or frame to reach the destination from the source. 20 milliseconds. So if one is sent at 1 millisecond, 2 is sent at 2 milliseconds, 3 is sent at 3 milliseconds, or all of them are sent at once. All of them are sent at once. But at the destination, what happened is 1 is received at 20 milliseconds, after 20 milliseconds. 2 is received after 28 milliseconds. 3 is received after 20 milliseconds, same as 1. 4 is received after 22 milliseconds. They belong to the same piece of data. They are all same data broken into pieces. When the receiving side, look at the receiving side, there is a jitter. What is this jitter now? Though they were at the same time transmitted, at the receiving side, the frame that started first, of course, came first. The frame that started third also came first. But the frame that started second was delayed. This kind of disturbance is called a jitter. Even this is also wrong for receiver. Receiver, this is a headache. This is improper flow, isn't it? Right? So 4 flow characteristics. I think I should log the meeting. People are just joining now. Give me 1 second, please. Right, can you see it? So 4 flow characteristics. Reliability is needed, delay, less delay, no jitter, high bandwidth or required bandwidth has to be given. Done. Let's go now. Now, these are very simple techniques to improve quality of service. Of course, the first 2 techniques could be theoretical, but the next techniques will be really, really interesting. Generally, they are like our real-time implemented things in our home. So they'll be very interesting and very easy to understand. So now in section 24.5, in the previous section, we tried to define what QoS is in terms of characteristics, 4 characteristics: bandwidth, delay, jitter, and what was the first one? Reliability. Right? In this section, we discussed some techniques that can be used to improve the quality of service. So those characteristics will define actually, but we want to now show some techniques to improve this quality of service. There are 4 types. The techniques now we are going to discuss fall into 4 categories: scheduling, traffic shaping, resource reservation, admission control, or the 4 strategies that we are going to discuss from now. Right? Now let us first talk about scheduling. What is scheduling? Now CPU scheduling algorithm from OS. CPU scheduling algorithm. What is the scheduling algorithm there in OS? Out of the available processes, which process should get executed first, and then which process should get executed next, and then which process should get executed. We had different algorithms. You remember? First in, first out. Shortest job first. Shortest remaining time first.
With Laravel.
Yeah, there were different algorithms. Because each algorithm had a disadvantage, we went to the next algorithm, and then we had to analyze the next algorithm. We wanted to find out the least waiting time and least turnaround time. No delay, less delay. That's what is here, right? Similarly, here also, if a data is being sent from source to destination, it should go through intermediate routers, right? Let me quickly draw a small diagram so that it becomes easy for you. Look at this. Let us just assume that there is a source. It is hard to right? Let us just assume that there are n nodes connected with lot of routers in between. Nodes connected with routers in between. Now, at the same time, A could be communicating with B, A could be communicating with C, A could be communicating with D. So, at the same time, B is communicating with D. A is communicating with C, B, D, and B is communicating with D. Look at what happens to this router here, There is data that is traveling from A to C. There is data that is traveling from A to B. There is data that is traveling from A to D. There is also data that is traveling from B to D. Look at the data packets that are coming to this router, and one data packet is from this side to this side. It should be routed. One data packet to this side, one data packet to this side, the other data packet from this side to this side. There will be a lot of incoming data packets, and they have to be scheduled properly at a particular node, right? That is what is flow, right? There is a flow of packets, and they are being monitored, maintained, and sent accordingly, right? So how that is scheduled, that is what we are going to discuss now. How exactly scheduling happens with all those incoming packets. How are they scheduled and how are they sent out? Did you get it? Did you understand that? All the data packets coming from different directions to that one particular node, how are they scheduled, one after the other, or however they are, and how are they sent out? That is what we are going to discuss in scheduling. That is flow control now, to improve quality of service. Some scheduling techniques to improve quality of service include, I have given 3. There are a lot of techniques, but in our syllabus we'll only go with 3 of them. They are called as FIFO queuing, priority queuing, weighted fair queuing. Then what is FIFO queuing? Look at it. Let us assume that this is the node. This is the node. Now before the node there is a buffer. Can you see? Incoming is arrival. There is a buffer. Let us assume. Is the buffer full? Question mark. Is the buffer full? Yes. Look at, there is an arrow going downwards. Yes. Can you admit a new packet into the queue? Which means the queue is full, right? You cannot. There is congestion now. Which means there is congestion. Now discard the packet. No, the buffer is not full. Push it into the queue or move it into the queue. Insert it into the queue. Send it into the queue. Now, out of those packets that are coming into the queue, there is a processor now. Now the processor picks one after the other. In which fashion? First in, first out. That is FIFO queuing. First in, first out. See this. If the packet here, packets are coming from A to C, A to B, A to D, B to D. The first to arrive is from C. Next to arrive is from B. C to, is there anything from C to D? Okay, we don't have it. First to arrive is from B to D. Next to arrive is from A to C. Next to arrive is from A to D. So then now they are pushed into the queue. First it takes the packet that has come from B. It looks into the header. I'm talking about routing now. It looks into the header. It identifies, acha, the packet has come from B. It is intended to reach D. Source address is B. Destination address is D. So it routes. It sends. Then it takes this packet. Source address is A. Destination is C. It routes to this side. Then it takes the next packet. Source address is A. Destination is D. Again, the third packet is routed to this side. So it is simply how the device manages the flow by using a queue. Before the data is processed, they are put into a queue, and that queue is called as FIFO queue. What is a FIFO queue? First in, first out queue. The packet that comes into the queue first is processed first and sent out first to the destination, in the direction to the destination. That is a FIFO queue. Here it is. There is a diagram there itself. A simple FIFO queue. Then a priority queuing. What is the difference between your FIFO CPU scheduling algorithm and priority scheduling algorithm? Whichever process has arrived first is scheduled first in FIFO. Is it the same thing in priority?
No.
No. Whichever process has high priority is processed first. అక్కడేమో OS లో ఉన్న ప్రాసెస్ గురించి మాట్లాడుకున్నాం ఇక్కడ జస్ట్ విత్ ఇన్ వన్ డివైస్. Now I am talking here, it's the same thing, but I am talking about the data that is going from one device to the other device in the network, and there are n such data packets that are coming to one router, to one device. All of them have to be maintained, monitored, flow has to be checked and sent. ఎవరి తర్వాత ఎవరిని చెక్ చేసి పంపించాలి, ఎటు పంపించాలి? FIFO అయితే ఫస్ట్ ఇన్ ఫస్ట్ అవుట్, ఫస్ట్ ఇన్ ఫస్ట్ అవుట్. But if it is priority queuing, here it is. The packets that are coming in are put to a classifier. Classifier will check the priority of the packets. Do you remember there is a field called PRI, priority? Leave it. Right. So it checks the priority of the packets. A high priority packet is put into a separate queue. A low priority packet is put into a separate queue. There will be two queues. High priority queue and a low priority queue. Every high priority packet is put into high priority queue. Low priority packet is put into low priority queue. Can you see this there? Classifier has two outputs. One output is going to one buffer diamond. Second output is going to second diamond. In both the diamonds, if it is full, simply discard. If any queue, if it is full, simply the incoming packet is discarded. What happens if a packet is discarded? What happens if a packet is discarded?
Congestion.
Because of congestion, whatever reason, it is discarded. Okay, congestion is there. Excellent. Congestion is there. Then what happens?
Data loss.
Data loss. Then?
Retransmission.
That's it. Simple. That is where your ARQ techniques come in again. Repeating requests, come in again. Okay. So we are now going slowly. We are going very deeply into the concepts. Okay. Now let's go to the first queue. If that high priority queue is full, that buffer is full, discard. If not, put into the high priority queue. Every low priority packet that comes in is checked again. If the low priority queue is full, discard. If not, put it into the low priority queue. Now I have two queues, a high priority queue and a low priority queue. Look at the processor. A processor now has a gate, a logical gate. To which queue it is first connected? Pink line.
High priority.
High priority, obviously high priority queue. Why? Because those packets are having high priority. They have to be processed first. They have to be sent out in the direction first. So it keeps processing one by one from the high priority queue. Then look at, there is a dashed line. From the pink line, there is a dashed line. That the switch turns to the other queue when the current one is empty. So when does this switch go to low priority queue?
When high priority queue is full.
When high priority queue does not have any packet to be forwarded, then it goes to low priority queue. What does happen here? What will happen here? There is a problem here. There is a name that I have given you in OS. When a low priority process keeps waiting for a high priority process to get executed, and it keeps waiting.
Deadlock.
Deadlock is a situation
Timeout.
where timeout, deadlock, there is a name for it.
Waiting time.
తినడానికి తిండి కావాల్సినంత తిండి, sorry, I've given this example. You remember there was a starvation. Thank you, sir. That was, yes, I've given you that example. అన్నదానం జరుగుతూ ఉంటది, అందరు తింటా ఉంటారు కానీ ఒక బెగ్గర్ వస్తే మాత్రం పక్క కూర్చోబెడతారు because he is having low priority, but he is starving. Actually he is dying with hunger, but nobody will allow him to come and eat. Go sit aside, you can eat later under one, because of low priority. It's the same thing here. Low priority queues, packets die of starvation. Time out avada akkada agipoyi unte. Yes, right? So this is the disadvantage. But if you go back to first in, first out. What is the disadvantage here? If a high priority packet has come after 5 or 6 low priority packets, is it given the priority? Here.
No.
No, it has to wait. So a high priority packet may have to wait in FIFO queuing technique. We solved the disadvantage here by using 2 queues, a high priority queue and a low priority queue, but it has aroused to a new problem called as kind of starvation, where a low priority queue can get easily filled up and the packets can get discarded, and the sender may have to retransmit the packets again, which in turn can cause congestion again. More retransmission obviously can cause congestion again, right? So that is the advantage and disadvantage of priority queuing. So now first one is not good, second one is not good. Both of them are not up to the mark. Though they have advantages, they are also suffering from some disadvantages. Let's go to the third, the last one. It's called weighted fair queuing. Before I talk about this, do we have time? Yeah, we have a lot of time. Before I talk about this, I want to talk about a very general example that happens outside. Listen to me, at least I'm talking about something that is not a part of your subject. Listen. Did we go to banks or did we go to some places where we have to stay? DMart, the best place. I think almost all of you have gone to DMarts, right? The biggest problem in DMart is not shopping. What is the biggest problem? Can someone tell me who?
Billing.
Even I faced it once. I never go to DMart, but once I was forced to go with my wife, and then I understood that there is a queue. That is what we are talking now. Now, sometimes what happens is we look at the queues before we enter into a queue. There are a lot of counters, right? 4 or 5 counters which are billing, and we look at each counter. There are 4 members. Here I have 5 members. There I have 2 members. Chalo. Where would I go?
2 members.
2 members. But what happened to my generally talking, it's not the case, but what happened is, though there were only 2 people, the person on the counter is very slow. Processor is very slow. He is scanning one item in 1 minute, whereas there were 5 people on the other side. The person is too fast, 10 times faster. That is the first thing. Second thing, the number of items that these 2 people are carrying are abundant, too many. The number of items those 5 people are carrying are very less. And after entering into this queue, how many times did this happen to us? We pick a queue and then we start feeling, I should have gone into the other queue. I thought this queue will get finished faster. Eppudanna jariginda itla? Not in DMart, anywhere.
Every time.
Yeah, every time, yes. It does happen to a lot of people for a lot of times, right? But if you go to, because I've been to Australia, in that place, in that country, in a lot of countries, you know what? You are not allowed to pick a billing line. You are not allowed to go to any counter. Though you have 10 counters in front of you, there will be 1 line. Only 1 line. Everyone has to queue in that single line only. That line will be far from the counters. Whichever counter gets freed, the next person, the first person in the single queue should go to that counter. Then the next person will become the first person. He will not or she will not pick the counter, should stay there. The counter will pick this person. The processor will pick this person. Whichever counter gets freed next, this person should go to that counter. Don't you think this is fair enough? This is much better than what you are facing, right? You pick a counter and that becomes delayed. Instead, this is much better, I guess. Even if you go to banks, it's the same system. You should not pick a counter. You should just stand in 1 queue. Whoever teller gets freed will call the next person, next customer. For example, if I call that as a queuing, that is single queue, but weighted fair queuing. You are giving a fair chance to everyone there. Everyone has to wait for the same amount of time. Did you get it? Queue gurinchi kada.
Sir.
Yes, but that queue is not the case here. But that is an example of weighted phase queuing. That problem can be solved in our DMART. I tried, I think if I go 2 more times, I'll try telling them.
Place a
Like,
cut.
weighted fair queue should be implemented there, right? We should tell them. Okay, now, some people are more smart. They put their trolley first and then they go shop for few more items. They want to get, forwarded in the queue. Right, anyway, we have all these problems, right? FIFO queuing had a problem now. Priority queuing also had a problem. Then we came up with this new solution called weighted fair queuing. Now in weighted fair queuing, what happens is there will be multiple queues. I gave you a general example of single queue, that put it aside just to understand it. Now here there will be multiple queues in weighted fair queuing. Every queue is given with a weightage. The number. Highest the number is highest the weight, which means high priority. Same, but high priority. But let us see the difference in processing. Weight, I have 3 queues in my example. Can you see the classifier with 3 queues? There is one queue with 3, 2, and 1. Weight is equal to 3, 2, and 1. So weight 3 has the highest priority. Weight 2 has the second highest priority, and weight 1 has the last priority here. According to the priorities, the incoming packets are queued into either 3, 2, or 1. Any one of them. The difference comes here. To your priority queuing and weighted fair queuing, the difference comes here. Instead of executing all the packets in the highest priority queue, it will not. It will go round robin. Do you remember round robin now? Round robin CPU scheduling algorithm.
Yes, sir.
Yes.
It gives equal priority to all the processes. It gives time quantum to each process and then goes to the next process, whatever the priority it is. Similarly, if the processor executes one packet from weight 3 queue, for example, one packet, and stops, it goes to weight 2 queue, it executes only one packet, not more than one. Again, it goes to weight 1 queue, executes only one packet, again comes back to highest priority weightage. If it executes 3 packets from weight 3, it goes to weight 2, again 3 executes 3 packets, so same number of packets in weight 1. It goes round robin, but the first choice is given to the highest weightage queue. It definitely goes round robin. But the highest priority is given to the highest weightage. From there, it gives the same chance of time or the packets for each queue. Do you really think there is a problem in this? Priority is achieved. At the same time, starvation is eliminated. See, I have written there above on the top right side, the turning switch selects 3 packets from first queue. My mistake. According to the weight, and here is a small change I wanted to make. According to the weight, if weight is 3, it picks 3 packets. If weight is 2, it picks 2 packets. If weight is 1, it picks only 1 packet. So it is giving high priority, more number of packets. At the same time, it is not waiting there. It is going to the next high priority, less number of packets, to the next least high priority, and then less number of packets, even less number of packets. At least it is giving a chance to the low priority packets. That is weighted fair queuing. Okay. So this is scheduling, only scheduling. We should now talk about scheduling, traffic shaping, resource reservation, and admission control. We are now done with scheduling. I wanted to finish all of them in today's class, but I have to take another class as it is Wednesday. I have a continuous class after this. I'll finish in the next 2 minutes. Srija, I have made you co-host.
So, okay, so I'll take the attendance.
Not now. Is the session logged? I have logged it, right?
Yes, logged, sir.
Yeah, when I tell you, do take it, please. Not now.
Okay, sir.
Okay, right. So this is about weighted fair queuing. Now let's go with traffic shaping. This is one good algorithm which should easily get into your brains, easy to understand. Now earlier we were talking about queuing the packets. How should you take care of the flow? Now we are going to talk about how to shape the traffic. For example, when you're coming to college at 9 o'clock in the morning, the road will be full busy. While going home at 4 o'clock in the evening, the roads will be full busy. But 1 o'clock or 2 o'clock in the afternoon, the roads will be normal. 4 o'clock in the morning, the roads will be completely idle. Especially 2 o'clock in the midnight, nobody. What does that mean is, it is called as bursty traffic. At some time, the traffic is very high at once. At some time, the traffic is really low. At some times, there is no traffic at all. But if at once there is a lot of traffic in the network, don't you think there becomes congestion? And at a time there is no traffic at all, there is no chance of congestion. So how to shape this traffic? How to solve this problem of bursty traffic at peak stages? At times there could be a lot of traffic coming into the network. How to solve this? This technique is called traffic shaping. And the algorithm is very simple. It's called the leaky bucket algorithm. Bucket is really good, right? You turn on a tap, it is a flush of water that is coming out of it. But if you put a bucket under it, it keeps collecting how much fast or slow the water comes. The bucket keeps collecting the water. Put a small hole to the bucket. The rate of incoming, if it varies, it gets less, it gets more, doesn't matter. It still fills into the bucket. But the rate of outgoing is through that small hole. It is constant. Look at the diagram itself should give you the clear idea. From the top, the water is coming. It could be bursty. Sometimes the tap is on, sometimes the tap is off. Sometimes it is less water coming, sometimes it is more water coming. But all of them will go into a bucket, a pool. From there, there is a small leak. Look at the water that is going out of the bucket, fixed flow. Look at the water that is coming into the bucket, bursty flow. So we will implement an algorithm called leaky bucket algorithm. How fast or how good or how bad the inflow of the data is, the outflow will be constant. Accumulate them, send them at a constant rate outside so that the network doesn't get congested. That is called a leaky bucket algorithm. You can see the diagram beside the bucket there. You have two diagrams. At some time there was 12 Mbps traffic. At a time there was only 2 Mbps traffic. But now on an average, the leaky bucket algorithm has made sure that it is constantly 3 Mbps. Load on the network is shaped by using leaky bucket. Right. Look at this is the implementation of leaky bucket algorithm. Every arrival packet, Srija, can you quickly take screenshots of the participants, please, and send it to me?
Okay, sir.
Yeah. Every arrival packet, it is put into a queue. How fast, how good, how big the number of packets that come into the queue doesn't matter. When they are going out, look at the yellow rectangle, remove packets at a constant rate. How many packets come in at what rate doesn't matter. At a constant rate, the packets are removed out and processed. This is called leaky bucket implementation for traffic shaping. Leaky bucket algorithm for traffic shaping. Okay. Next is traffic token bucket. We'll stop with this leaky bucket algorithm. A leaky bucket algorithm shapes bursty traffic into fixed rate traffic by averaging the data rate. It may drop the packets if the bucket is full. Obviously, always if the queue is full, the packet that is coming in is dropped. Right. So with this, I'll stop. We still